Now, quite often it's actually kind of easy to identify what kind of problem is being asked. This is obviously to do with projectile motion. You've been given a speed and a velocity. So kind of imagining that you've got 43 degrees to the horizontal, and that's traveling at 18 meters per second. So you can work out the horizontal component and the vertical component. Now the vertical component is what you're interested in terms of the initial velocity. So that's simply going to be 18, okay, and times by, now you're interested in this side, so it's going to be 18 times sine 43 degrees. So if you do that on your calculator and you enter sine 43, okay, so in sine 43 equals 12.27 meters per second. So that's the velocity up there. Now we can actually work out the horizontal one, which quite often you need later anyway. So cos of 43 times by 18, and that equals 13.16 meters per second in that direction. So the time to the peak. Now if we look at that, actually we'll do this first because obviously it's the maximum height we're looking for. So we know that the initial velocity, so it's going to be 12.27. We know the final velocity at the peak is going to be 0. We know acceleration is equals minus 9.8 meters per second. And if we look at the formula, the one that kind of makes sense is Vf squared equals Vi squared plus 2AD, because the D is going to be the distance we're interested in. Okay, so if we kind of get rid of some of that stuff, and now have a go at the actual calculation. So 0 equals 12.27 squared. That's minus 2 times 9.8 times by D. So then that's going to equal 12.27 squared, which is going to be, and that equals 150.55, minus 2 times that equals 19.6 times D. So if we then, actually that becomes positive because we can move that over to the other side, so I just did that in one step. So then that just becomes 150.55 divided by 19.6 equals D. And that equals 7.68 meters, which if you round it to 2SF is 7.7 meters, and that's that answer. Now the time to apogee, the time which is the peak, is Vf. So Vf is going to equal to 0. Vi equals 12.27. I've already used that. Acceleration equals minus 9.8. So we can do this without having done the previous one, just by looking at Vf equals Vi plus At. So it's 12.27 minus 9.8 times T, Vf equals, so that then becomes 12.27 equals 9.8 times T. 12.27, oops, that's a bit of a mess, 12.27 divided by 9.8 equals T, so T equals, and that equals 1.25 seconds. Okay, so that's that answer. Now the horizontal distance is simply going to be the horizontal speed, which is 13.16 meters per second. It's a horizontal velocity, and just however long it's going now, it's 1.25 seconds to the peak, so therefore it's 2.5 seconds in total, so that just times together, and that equals 32.9 meters or 33 meters to SF. Now, this is a torque and equilibrium problem. And one of the things you normally have to do is identify where the forces are. Now, there's a centre of mass coming down there, which is the mass of this plank through here. So the centre of this, because it's 3.15 metres long, is 1.57 metres. So it's 1 metre from here to here, which means it's another 0.57 metres to there. So that means the mass of this going down is going to be the weight force of the plank, which is 14.5 kgs times 9.8. And then if we're talking about torque, how far away is it from the turning point? So if we're choosing this as our pivot in the middle, which is the logical thing to choose, that means this is causing it to go that way. And how far is this from the pivot point? Well, it's from this distance to this distance, which is 0.575 meters. So that will give you the torque in one direction. And then the weight force of this guy times the distance will give you in the other way, and they've got to be equal. Now, obviously, we're trying to work out the distance. So the first thing we do is multiply those three together, and that equals 81.7 Newton meters. Now I'll just get rid of this here, and that's got to be equal to the torque in the other direction, as it's in equilibrium. So we've got the weight force of this guy, which is, was it 55.6 times by 9.8, and then that's going to be times the distance here is from the pivot point. So if we multiply that together, the 55.6 times 9.8, we get 544, that's wrong, 544.88, 81.7, and times D. So if it becomes 81.7 divided 5 by 544.88, and that equals something that equals D. If you do that calculation, you'll find it's something like 0.149 meters, which is approximately 0.15 meters. So it's only about 15 centimeters from the end here. So that would be as far as you could go without it tipping. Okay, and that's the first torque and equilibrium one. Now this problem is a little bit more involved, and quite often they wouldn't give you as much information. So for instance, you know, you've got to know the support forces are going up here, and what's countering them is, or you've got the weight force of the bridge going down, which is exactly at halfway. Then you've got the weight force at the for the truck itself, which is, you know, depending on where it is, will depend on what that is going to be. So you've got those things to consider, and obviously the length through here. So you can choose either point, but I think this is an easier point to choose as a pivot. We've got the weight force going from this distance across. So how long is the bridge? It's 75 meters, so it'll be 75 divided in half, so that's 37.5 meters times the weight force of the bridge, which is times by 6 times 10 to the 6 kgs, okay, times 9.8. Okay, so that'll give one of them, plus the actual truck itself, which is 10 meters from the end, so it's 10 meters, times by 3.6, so this is the mass of the truck itself, and again times 9.8. So we're kind of going to have this going this way, this going this way, and what's countering that in the other direction will be what we calculate for the support force for the other side. So if we work that out and we multiply this through, we get this number. It is in Newton meters. That's one of the torques. We work that one out, we get that one. So that is causing it to rotate in one direction. Okay, so if we still consider that, what is the one going the other way? Now, that means countering that. Now, that's the torque in one direction. Now we're talking about the torque coming from this. So this is going to equal FA times the distance of 75 meters. So if you divide this by 75, you should end up with, so you can divide this by 75 over here, that will end up being equal to 2.94 times 10 to the power of 7 newtons. I think that's right there. Yep. So that's that force. Okay, but if we need to work out the force on this, that's going to be a little bit different. So the combined weight force of the truck and the whole bridge minus FA will give us FB. So if I write that out over here, so that's going to be FB will equal the weight force of the truck. So I've just written that out there, but so basically the down force equals the up force. And as we know, the total down force, which is just the weight of the bridge, sorry, that's the weight of the bridge on that side, and the weight of the truck on that side, and we subtract this, one of the support forces, that must equal the other support forces, because both support forces must add up to this combination over here. So if we just go through and work that out, we should have an answer. So in setting this up, we've just added up, that's the weight force of this, combined with the weight force of this, so just multiplying by gravity. And then we add them to get this, and we're going to subtract FA. So if we do that, we're going to end up with 2.975 times 10 to the power of 7. So if we do that to just 3, see if that's 2.98. So the support forces aren't that different. Okay, so that's going to be FB. We'd expect that to be a bit more than this because it's closer to that support on that side. So those are your combined answers there anyway. So that's that problem. Now vector problems can be either kind of simple or they can be kind of hard. And sometimes it's even the question that can just be confusing. So you have to really figure out what's kind of happening. Now, for instance, this guy is pulling away at the sled, and we've used this example before, but even because he's pulling at an angle through here, not all the force is going to be useful in terms of moving it forward like this. So it will move forward, but all that 450 newtons. So if we wanted to know the force going in this direction, we just have to use a bit of trig. Now, this is obviously a lot more simple. So the net force going in this direction, if there's no force coming back this way, is simply going to be 450 times by the cos of this angle, which is 38 degrees. So that's fairly straightforward. Now, there would be a force going in this direction as well, which I'm not too worried about, and that would be an additional support force, because that's kind of helping to lift this. So that combination of this and this here should balance with the gravitational force down there, but the question really isn't asking this, it just wants the kind of force going in that direction. So that's simply going to be 450 times. Now that's the net force, and we'd expect it to be less than 450. Okay, so it's 355 newtons going in this direction, or to the right or to the east. So that's the net force. Sometimes the vector diagrams you're being asked to do might just be the kind of head to tail ones where you add them, or if you do a subtraction to get the answer. In some of the cases it's really just setting up a triangle that you can then solve for a net force. Okay, so the next one. Now we've got a weight force from this object of 88 newtons going down, right? Now if this was just being supported this way, if this was a piece of rope just hanging straight down, that would be 88 newtons just going straight back up. But it isn't. For a start, it's shared between two, so we can consider it to be 44 newtons as it's equal on either side, and it's at an angle, so the force that's going to be needed to support that's going to be greater. Now if we redraw this diagram, okay, we've got something like this, where we've got 44 newtons force, because that's the 88 split in half, because there's 2 ropes. But obviously the tension's coming through here, and there's an angle of 30 degrees. It's a terrible diagram, but anyway. And that means that we can work out, we just want to work out what's the force in this one, which we would expect to be greater than 44 newtons, because it's being applied at an angle as force. So it's adjacent. This is what we're interested in here. So cos of 30 degrees equals adjacent over hypotenuse. Now the adjacent is 44 newtons, which is that one there, and the hypotenuse is what we want to know. Now obviously if we switch that around, x equals 44 newtons divided by cos 30. Now cos of 30 equals 0.866, so 44 divided by 0.866 equals 50.8, or 51 newtons. So that's a tension force in both strings. Sorry, that's in each individual string. Now in this case, we've got a net force of 2650, so that's causing it to accelerate in this direction. But the wind's actually blowing in that direction, so it must be a greater force than this, because some of the force is going to go in other areas. But basically, we need to work out what that is. We've got an angle of 48 degrees, so this is again a bit of trig, and we can redraw this as well. Now I've got 48 degrees here. This is what we want to know. What is this force here that's being applied to make it go? And it's got to equal that. So that's a hypotenuse. This is not the adjacent angle, so it's opposite over hypotenuse. So the opposite is 2650 over the hypotenuse, which is x, and it's going to be sine 48 degrees, and we can solve it that way. So it's going to be x equals 2650 over sine 48. So if we then carry on and solve that, it's 2650. If I did that right, I'll just check. 2650 divided by 0.743. 3566 newtons. Now if that was 2ECF, that would just be 3600 newtons. Okay, and that's that one.